is the first video of a course I'm going to be doing about axiomatic set theory. Specifically the axioms of Zermelo-Fraenkel set theory, or ZFC. The C in this case stands for an axiom that was kind of controversial at one point called the axiom of choice, which is, well, it's going to be a bit down the road for us. But in order to talk about this series, you should probably already have an idea of what a set is. I mean, not axiomatically, but you should probably have some minutia with it. Say a set of real numbers, a set of integers. You probably should have studied some functions between these sets already. This really isn't a great source for a first introduction to this idea. It's also pretty recommended that you already have experience with formal proofs and propositional logic, because again, this might be a little bit terse for a first introduction to these things. Now, the text that I first learned set theory from is Introduction to Set Theory by Hrbacek and Yek, and I think it's a pretty decent textbook, and it's going to, at least for the beginning, form the basis of some of the things we're going to talk about. We may jump around later. Now, what about this particular episode? Well, this first video is really just a brief introduction about, well, why we would care about sets in the first place, why we should study this formally, and sort of ideas about set theory as a foundation for mathematics. It's maybe even semi-historical. So that is, if you're already well inspired to get into set theory, you may feel like jumping to the next video, which is where we really start laying down the axioms and getting into the thick of it. But without further ado, for those of you who want the introduction, it's time to travel to the Platonic realm! The first thing I want to discuss in regards to why study set theory, or why we need a formal set of axioms, involves what's called Russell's paradox. You may have heard of this before, but we're going to review it. So Russell's paradox shows the pitfalls of what can happen if we just work with a naive set theory that isn't bound by any sort of constraints of an official axiomatic system. So the paradox goes like this. We define a set R, and this set is going to be the set which contains all other sets, X, such that X does not belong to itself. Now this seems like a pretty reasonable thing to think about. So we know that we can have sets that contain other sets. For instance, I could make the set which contains 1, and let's say it contains the set 2 and a square. Right, so a set is just some collection, some sort of bag of stuff from the perspective of naive set theory, and so it can include even other sets, right? So the fact that R is a set which itself contains sets, nothing wrong there. And the demand that the sets belonging to R do not contain themselves, that's also very reasonable. It's pretty hard to come up with an example of a set that contains itself. For instance, if I had the set that just contained 1, and I wanted to try and make a set that contained itself, well, I could try and put this set 1, the set containing 1, inside of itself. So I would still have the set containing 1, and inside of that would be the set containing 1. But now this set doesn't, the set referring to that which is the outer curly braces, this set doesn't actually belong to itself, because this is now the set which contains both 1 and the set containing 1, and what's actually inside this set is just the set containing 1 and 1 itself. Now, this may give you an idea to try and make some set where you had, say, the empty set, and then ... just infinite nested braces on either side, creating some set with infinite braces both ways. And okay, this looks like it could be a set which contains itself, but this is pretty unnatural. And in any case, the point is that having this condition, asking that a set not contain itself, seems pretty normal. This is basically saying, let's just group all the normal sets together. And those are typically the ones we want to talk about anyways. The issue pops up when we try and ask ourselves a question. And that is, does the set R contain itself? So here's how the argument goes. If this was true, if it was the case that R was contained in itself, that means that it has to obey the rule that it does not contain itself. And so it must be the case that, in fact, R does not contain itself. So this seems like a paradox right here already, but this isn't actually a big deal. It would be contradictory for R to both contain itself and not contain itself, but we've just shown that this sort of contradiction only arises if we first assume that it does contain itself. Okay, so no big whoop, that seems ridiculous. So it's got to be the case then that R does not contain itself, right? That's got to be the conclusion that we have to draw. But here's the catch. If R does not contain itself, then that means that it does obey the rule, which is the defining feature of the set R. And if it obeys the defining feature of the set R, that means, by definition, that R must belong to R. In other words, if R doesn't belong to itself, well, then it does belong to itself. Now we've got ourselves a problem, because we have that R belongs to itself implies that it does not belong to itself, and if it does not belong to itself, it does belong to itself. In other words, R belongs to itself if and only if it does not belong to itself. We now have a problem because this is equivalent to saying that the set R must not contain itself and it must contain itself simultaneously. So this can't possibly be true. First off, this seems frightening for all of mathematics because somehow we've logically derived some sort of contradiction. We've exposed a hole, a paradox in the logic of mathematics itself. And the other fact being is that not only is a contradiction bad enough in itself to have in your theory, well, the very reason why a contradiction is bad is because it follows from any false statement, you can prove any statement whatsoever, Q. And this is essentially why we don't like contradictions, because from a contradiction you can derive any other statement, and that makes a theory useless. You can prove every single statement true or false. And this is clearly not the sort of logic we want to work with. The other reason why we want an axiomatic formulation of set theory is as a foundation for mathematics. By this I mean a lot of the objects that mathematicians work with, and pretty much at the time of the foundation of axiomatic set theory, all of the objects that mathematicians worked with can really be phrased in terms of sets. So the natural numbers form a set, but even the natural numbers themselves can be described in terms of sets, as can the real numbers, the complex numbers, etc. And lots of times, whether we're studying, say, topology, or we're studying group theory, really what we're doing is defining objects in terms of sets and studying functions between them. And one of the things we're going to see in this course is that functions themselves can be described as sets. So we'll sort of notice that a lot of these things can really be put in the framework of set theory. And one of the other things that we do in mathematics is we prove things starting from axioms, which are baseline assumptions. So with any rigorous logical argument, of course, no fact can truly just be derived out of nothing. You have to have some assumption at the bottom of it all. And the idea is, in order for mathematics to have the greatest amount of objectivity, we really want to have a scant collection of axioms. We want to keep it really slim and be able to derive as many mathematical truths as we need from those bare bones axioms. And so one of the things that we can do in set theory is a good portion of modern mathematics can all be traced back to foundations in set theory. So the list of the axioms of what's called ZFC set theory are a list of 7 to 10, depending on which axioms you're using, assumptions that describe the most of modern mathematics. Now, of course, there's other things out there like type theory, or homotopy type theory. Maybe homotopy is a better way to pronounce that. There's also things like category theory. And there's also different kinds of set theories too. It's not just ZFC. There's other sorts of set theories out there. But even given the usefulness of these other ways of looking at and organizing mathematics, ZFC still encapsulates a lot of what the working mathematician does on a day-to-day basis. So, with that in mind, that wraps up this short introduction, and we can get moving on to the meat and potatoes. I'll see you for the axioms in the next episode. Be sure to leave questions, comments, concerns in the comments. We'll try to get back to you, and hopefully it will inform me to make better episodes in the future.